session. Earlier in the week, we were commiserating about how difficult this task seems. I took some comfort in that in my struggles to prepare my own talk. But it turns out their talks were great, and it's good for them, and it's good for you guys, but it's not so good for me. So there are two rather different aspects to the relationship between quantum chaos and gravity. One of them, you could call it coarse-grained chaos, basically has to do with studies of the butterfly effect. And this is something that's fairly easy to do in gravity. The other aspect, you could call it fine-grained chaos, has to do with the traditional subject of the study of quantum chaos, spectral statistics and fluctuations, and this seems to be difficult in gravity. And I'm going to sort of touch on both of these subjects. In part one, which is not, I should mention, going to be overflowing with vision, I'm going to sketch some recent work by these people on a type of post-out-of-time order correlator perspective on the butterfly effect and gravity. And then in the second part of the talk, I'm going to discuss some thoughts related to gravity and late-time chaos, motivated by the talks earlier in the week by Steve Schenker and Edward Witten, and the poster by Phil Sod. So this post-OTOC notion is sometimes referred to as the size of an operator. And I don't think it's known how to define this in a general quantum system, or especially not in quantum field theory, but we're going to work in the Hilbert space of n Majorana fermions, which satisfy this algebra. And the size of an operator is just defined to be the number of these basic Majorana fermions that you need to multiply together to form the operator. So for example, psi1 is an operator of size 1. This thing over here is an operator of size 3. And we would say that this operator O has probability 1/2 to be size 1 and probability 1/2 to be size 3. So we can define the expectation value of the size S of O as being 2 in this case. The size of an operator is directly a measure of the influence that it can have on other simple degrees of freedom in the system. And if the size is of order n in particular, then this operator has an order 1 influence on a macroscopic fraction of the degrees of freedom in the system. This is sort of the endpoint of chaos, of the butterfly effect. Now, the basic phenomenon underlying the butterfly effect in quantum mechanics is that simple operators grow under Heisenberg time evolution. So for example, if we take the SYK Hamiltonian, then a commutator with H turns a size 1 operator into a size 3 operator. And I'm going to represent that with this notation here, where the 1 on the left refers to the index of the original fermion. This vertex here is the J tensor, and the exposed ends on the right here represent the fermions psi A, psi B, and psi C. So if we take a second commutator with H, then each of these fermions, psi A, psi B, and psi C, can themselves split into size 3 operators. And we get, in this way, 3 different size 5 operators represented here. Proceeding further in this way, one finds that at large n, the evolution of psi 1 of t is equivalent to a quantum particle moving on the graph represented here at left, where vertices in the graph correspond to fixed operators. And we start off at this left vertex here, and then allow the particle to propagate quantum mechanically on this graph. The size of one of these, the operators corresponding to one of these dots, is roughly the distance of that operator to the root of the graph. And under time evolution, that thing grows exponentially. Grows exponentially due to the linearly increasing degree of this graph. If you step into it k steps, then the degree, the number of vertices that you're connected to in the next generation, is proportional to k. That leads to exponential growth. Okay, so this is some picture for the growth of an operator. Now, the work that I want to tell you about starts in last fall, a paper by Xiaoliang Qi and Alex Stryker, who showed that at finite temperature, it's useful to define a type of thermally renormalized size for an operator. So we modify this definition in the following way. So let beta be the inverse temperature and rho of beta be the thermal density matrix. Then we define this thermally renormalized size as the size of the operator, O times the square root of rho, minus the size of the operator square root of rho itself. So this is sort of like the extent to which multiplication by O makes the thermal density matrix a bigger operator in the sense that we've defined it. This may not seem like a terribly intuitive definition, but I think it's quite a clever definition. And one of the reasons is that this spring, these people found a nice description of this size in the bulk theory for ADS2 using some previous work. And their conclusions resonated with the ideas of these people. So I want to tell you basically about one equation that they found. And to display the equation, it's going to be helpful to insert one intermediate step where we view the space of operators as the space of states in two copies of the system. So basically the way that works is you take an operator, a general operator like this, and you flip the bra vector around into a ket, and you can write it as an entangled state in two copies of the system. We'll call L and R for left and right. So time evolution acts on the operator O by conjugation, and that corresponds, using this map, to Hamiltonian evolution in this state, but with the Hamiltonian h right minus h left. Okay. So now to proceed further and understand the relation, the bulk formula for the size, we would like to understand the bulk states that correspond to these operators appearing in this formula. So first, in the holographic description, the state corresponding to square root of rho is this thermofield double geometry that was discussed by Aaron this morning, been discussed also by other speakers. This is an entangled state of two black holes. And the time translation invariance of the thermal state corresponds to the boost symmetry of this geometry. The state corresponding to this operator with an O is a state where we have some matter in the interior of the spacetime, represented by this blue trajectory here. This operator is not time translation invariant, and correspondingly the bulk state does not have a boost symmetry. Instead, if we make a time translation of this operator, we apply a boost to this matter propagating in the bulk. And if the time translation becomes large, the boost is large. The matter is very close to the horizon. Okay, so now we can ask, what is the bulk formula for the size of the operator? And the definition of size that we gave before in terms of these fermion counting is equivalent to the following operator acting on the Hilbert space of these operators viewed as states. So it's a two-sided operator acting non-trivially on both the left and the right system. And using this formula in ADS2 gravity, these authors showed, they actually showed a more general and quite beautiful formula, but a special case of it is that they showed that the growing part of the size is equal to a bulk operator we call P+. So that's the momentum going up and to the right in this direction. And technically, it's an integral of the stress tensor T minus minus across the other horizon, this heavy black line. So this is an average null energy operator, as Aaron refers to it, along this horizon. So this is the equation that I wanted to get to, and I think it summarizes in a really interesting way the relationship between chaos, represented by the left-hand side, and the gravity theory on the right-hand side. And I want to make just a couple of comments about it. So first, the time evolution of the two sides is explained by very different pictures. So they both grow exponentially under time evolution, which is good because they're supposed to be equal to each other. But the thing on the left-hand side grows exponentially because of this operator growth process, this chaos process happening in the boundary theory. The operator on the right grows exponentially under time evolution just because time evolution is a boost, and the Lorentz algebra tells us that the translation operator, null translation operator, gets rescaled by an exponential under boosts. So somehow the Lorentz algebra of the region near the horizon is emergent from this weird chaotic operator growth process happening in the boundary theory. So these people referred to this as order from chaos. There's a second point about this which is interesting, which is that the operator on the right-hand side, P+, is kind of a useful operator to think about in holography, because it can be used to translate things across the horizon. So it can move things behind the horizon of the black hole. And actually, the traversable wormhole protocol of Gao, Jaffress, and Wall can be understood as an application of this formula. Of course, their work was before this formula, but it could be understood in retrospect as using this size operator to move things behind the horizon of the black hole and make the black hole traversable. So the final comment I want to make about this before moving on is that it's interesting to think about how this equation will be generalized if we move to theories that don't saturate the chaos bound, or if we move to higher dimensional theories. In theories that don't saturate the chaos bound, the left-hand side will be growing slower as a function of time. And I think the way that must work is that the right-hand side we would replace this operator P plus by a non-trivial light ray operator in the bulk theory. In higher dimensions, it's not at all clear, at least to me, that the size of an operator should be a concept that makes sense in quantum field theory. But the fact that these light ray operators make perfect sense in higher dimensions suggests that maybe there's some analog. Okay, so now I'll move to the second part of the talk. And here we're going to start out by discussing the traditional subject of study in the field of quantum chaos. This is a sort of uniquely quantum mechanical aspect of chaos, unlike the butterfly effect, which has a good classical analog. So this uniquely quantum aspect of chaos starts with thinking about the statistics of the irregular discrete set of energy eigenvalues of a quantum chaotic theory. These things lead to erratic long-time behavior of correlation functions. So a very simple function to consider is just the analytically continued partition function, which is a sum over all of the energy eigenvalues of e to the minus beta plus it times the eigenvalue. And if you take a spectrum that looks like this and process it through this formula and take t to be large, you get a rather erratic curve that looks like this for large times. And a basic puzzle is that in a holographic dual, in a theory with a holographic dual, it's sort of hard to imagine how smooth geometry or simple concepts in the bulk theory can lead to such a chaotic signal. And this is something that's been discussed quite a lot in the literature by Maldacena, Barbon, Rabinovich. I also put Polchinski's name here because this was something that he was thinking about rather recently. And I think that he was bothered by this problem and seemed to think that it might be so hard to imagine how gravity could produce this type of signal that you could think about it as a type of argument for a fireball. Anyhow, even though for any particular Hamiltonian, we expect to have this erratic discrete set of energy eigenvalues and erratic correlation functions, if we take a suitable average, then one could imagine getting smooth functions that could be computed in gravity. So, for example, let's take this thing, this analytically continued partition function on the previous slide, take the square of it, and then average it over some samples, 1, 10, 100, or 1,000 samples of some theory like the SYK model or samples from a random matrix ensemble. And if you plot this function as a function of time, it looks like this. You can sort of imagine, well, it seems fairly clear that it's going to be approaching a smooth function in the limit of infinitely many samples. And if you look very closely at this fourth panel, you'll notice a small positive slope. That's because this is actually drawn from the ramp region of the spectral form factor that was discussed in Schenker's talk and also Swingle's. But it's kind of striking how much you're throwing out in going from this erratic, disordered curve to just this tiny positive slope over here. You're throwing out almost everything that is interesting about this function. But you could imagine that since this limiting smooth curve is simple enough, perhaps it could arise from an easy gravity calculation. And in fact, this is true, at least in some cases. So, as described in Steve Schenker's talk, in JT gravity, this JT gravity computation on this topology gives the leading approximation to the random matrix theory average of the connected correlation function of two of these partition functions. And this function can be analytically continued in beta 1 and beta 2 to give this small positive slope that we saw on the previous slide. It doesn't give the erratic stuff, but it gives this small positive slope. So I want to make two comments about this. The first comment, which will be relevant in a moment, is that this geometry here is not a classical solution of the JT gravity theory. What the action wants is it wants to make the tube longer and thinner. But JT gravity is simple enough that we can take off-shell configurations like this seriously, and we can do the integral over the modulus of this double trumpet. And it's the integral over that that gives precisely this random matrix theory answer. So it's important that that random matrix theory answer came from something that was not a classical solution. A second point I just want to emphasize is that this geometry is it's a Euclidean space-time wormhole. So explicitly the metric is this. d sigma squared plus cosh squared sigma d tau squared, where d tau is Euclidean time. It runs around the compact direction of this wormhole. And this should be contrasted with an Einstein-Rosen bridge kind of wormhole. That's a spatial wormhole. And Einstein-Rosen bridges in holography represent entanglement between two different systems, entanglement between states. Euclidean space-time wormholes like this are different. They represent correlation between partition functions, not between states. And there's a famous puzzle about this, because if we take a partition function of a fixed quantum mechanical theory, and we specify the inverse temperature, then z of beta is just a number, and it can't have a connected correlation function with anything. This was a puzzle that was discussed by Maldacena, Maus, Arkani Hamed, Orgera, and Polchinski. Basic puzzle is, it seems like Euclidean wormholes want to give you correlation between partition functions, but for a fixed boundary theory, there can be no such thing. Now, the results discussed in these talks earlier this week are only consistent, therefore, with JT gravity being interpreted as dual to an ensemble of boundary theories, where you can have a connected correlation function, because z of beta is not a number, it's drawn from this ensemble. Okay, so there are a few natural questions that I want to discuss about this. So this is the most obvious natural question, which was discussed by these authors. Why don't these Euclidean wormholes contribute for a fixed boundary theory? This seems like an important problem, and I don't have anything to add to the discussion in these papers, and basically there isn't a very good answer to this question that we know of. But I feel that this isn't really going in the right direction, but I feel that the work on JT gravity has made this question seem a little bit more pressing, even more problematic. And there are two reasons for this. So one point, which is, these papers were a little bit complicated. One of the reasons is that it's harder than you might think to find Euclidean wormhole solutions in the relevant theories of gravity. But in JT gravity, we didn't have classical solutions, and they still made an important contribution. So if the Euclidean wormholes don't have to be solutions, it's easy to imagine metrics that connect different boundaries together. We don't have to go through the hard work of finding an actual controlled solution. The second reason is that these Euclidean wormholes in JT gravity don't just give some kind of meaningless garbage, some kind of arbitrary thing. They give a very definite kind of answer, which is they reproduce the correlation functions of a random matrix ensemble. It's a very particular constrained type of set of correlation functions. So it's not like we're supposed to just always completely ignore these Euclidean wormholes. In at least some cases, they give answers that have some meaning. It's a meaning that's not consistent with a fixed boundary theory, but it's something that has some content. Okay. So a second question, which was discussed a little bit at the end of Steve Schenker's talk, is this question, where does the erratic chaos come from in a fixed boundary theory? Where does this erratic function actually come from in the bulk theory? And I don't have anything to add to that, but there were some ideas in Steve's talk. The final question, which I'm going to talk about a little bit, is the following sort of obvious question, which is, are there more quantum gravity theories like JT gravity that are dual not to specific quantum systems, but dual to some kind of ensemble average? And is there something wrong with this idea of a gravity theory being dual to an ensemble average of quantum systems as opposed to a single one? So if you start with JT gravity and you're trying to find another theory of gravity, you're working your way up gradually towards more interesting theories of gravity, your first stop is probably going to be 3D pure gravity. And in this context, this is one of the cases that was studied in the paper by Maldacena and Maus, and they pointed out that in 3D pure gravity, there are very simple Euclidean wormholes which look like this. D sigma is going left to right here, and this capital sigma is this genus 2 Riemann surface. So I took this figure from their paper, and it represents a geometry with two asymptotic boundaries that are genus 2 Riemann surfaces. So this type of Euclidean wormhole represents a type of correlation between partition functions But it's not thermal partition functions. They're partition functions on these genus 2 surfaces. On the other hand, this geometry here is a quotient of hyperbolic 3 space, so it's an exact solution to Einstein's equations. But we don't care so much about solving Einstein's equations. And a closer analog to the situation in JT gravity might be a geometry like this, where we have two tori connected by some kind of Euclidean wormhole. You can't find an completely on-shell solution to 3D gravity that looks like this. But you can imagine treating it like the double trumpet in JT gravity gets treated. One way to think about that is that you divide the integration over the bulk geometry into steps. First, you fix the size of the two cycles of the torus at the minimal point in the center of this wormhole here. You fix them to be some numbers. After fixing that, there's actually a on-shell geometry subject to that constraint. And then at the end of the day, you integrate over those lengths between 0 and infinity. This is similar to the method of constrained instantons in quantum field theory. So, and if you do that, go through that procedure, the computation of the action of this thing for fixed values of those lengths is very similar to the double trumpet in JT gravity. It looks like a calculation can be treated in a similar way. Now, there are more ways that this geometry can be off-shell than in JT gravity, and I'm not sure whether it's possible to evaluate the path integral here exactly. Maybe somebody in the audience knows. But this geometry suggests the following question, which I'm sure has occurred to many of you. Could it be the case that 3D gravity is actually dual to some kind of analog of random matrix theory for 1+1 dimensional CFTs? So this is something that you could call random CFT, if that meant something. Now, there's not an obvious candidate type of ensemble. In quantum mechanics, there's this nice ensemble of random matrix theory. And as far as I know, there isn't an analogously nice ensemble of random CFTs. But you could hope that by studying 3D gravity and thinking about it in this context, you might actually be led to understand a simple type of ensemble of theories. Okay. The final question I want to discuss is this one. So if we imagine that there are some theories of gravity that are dual to specific quantum systems and some theories of gravity that are dual to ensemble averages, then we should really be forced to confront the question of what could be different about them. How are you supposed to know if one is dual to specific boundary theory or an ensemble average? And a possible necessary condition for a theory to be dual to a specific boundary theory is that it seems like you might need to have microstates that allow you to break this double trumpet geometry. There are related comments in this paper by Harlow and Jafferis, and also in the earlier talk by Schenker. And the main thing I want to mention here is a possible clue from the bulk theory that UV properties of the bulk might be important in thinking about this. And that's the following. If you think about this double trumpet geometry, or a similar geometry, then the integral over the size of the wormhole in the middle here will include a region where it's long and thin. Actually, that's the region which sort of gives the dominant contribution to this path integral. And that means that there's going to be a short geodesic going in a loop around the center of the wormhole, and high-energy bulk states propagating around that loop will be relevant. So it could be that computations involving this type of thing could be very sensitive to the UV properties of the bulk theory. Now, I have 1 minute left, and I want to take this opportunity to make a brief comment related to this about some comments that were made after Ahmed Al-Mahiri's talk this morning. So there was an objection that was raised, which I think is a reasonable objection, which was that JT gravity coupled to matter is a UV-complete theory, and it leads to information loss. And in Ahmed's talk, he started with JT gravity coupled to matter, and he came to a different conclusion. Now, the point I want to make is that in Ahmed's talk, he ran into trouble with this Araki-Lieb inequality only in the case where the ground state entropy, S0, was finite. And that's a case where the topological counting parameter is finite, and presumably we should include Euclidean wormholes. And the point related to this paragraph here is that once you include Euclidean wormholes, JT gravity coupled to matter is actually not a UV-complete theory. And even if it was, the Euclidean wormholes would change the answer, and they would change the conclusion that was being discussed by, in the comments after Ahmed's talk. So I think that gives us sort of a response to the objections that were raised. But more interestingly, I think it suggests that it could be the case that Euclidean wormholes might be relevant to the derivation that presumably exists for using this non-trivial quantum extremal surface to compute the entropy. Okay, so thank you very much.
Okay, that was great. One or two questions for Douglas, and then we'll all come up and continue. But specifically, there's a very good question by...
Is this the daily double?
Sorry?
Is this the daily double?
David Double?
I feel like I'm playing Jeopardy or something. But...
No. Anyway, a question for you. Is gravity, which is related, is gravity dual to the average of quantum systems or to a definite quantum system? And second, could it be that in highly supersymmetric examples where we have been misled because there's only one Hamiltonian in the class that we should average over?
Well, I wish I knew the answer to this question. It was a lot of sort of the stuff that I was struggling with in the talk and in preparing it. If we imagine that that were the case, though, we would need to have some evidence of what these other theories are that we're supposedly disorder averaging over to produce a bulk theory that's a disorder average. And I don't know how to go about thinking about that, but well, you could imagine trying to ask the question in SYK. Something like this would be, is there an actual bulk theory for individual instantiations of the SYK model? And well, beyond that, I don't really have anything useful to say.
Okay. There was another good question for you, which is, let's see. Yeah, I think, well, there was, you might have the same kind of answer. Averaging, random averages in SYK gives rise to baby universes. Is the converse true? If there's no random average?
Sorry, if there's no random average, then?
No baby universes.
Oh, well, if there's no random average, then you can't have any, if you have the Euclidean wormholes, then they have to cancel somehow. So, yeah, I'm really puzzled by this problem, but I feel a little bit like I'm being asked the questions that I was asking myself in the talk, and I thought about it in preparing the talk, and I didn't come up with more to say than I said, so I apologize for not saying much more.
That's all right. This is not a quiz.
It feels a lot like it.
This is...
I got my buzzer here, and
right.
I'll take quantum chaos for 200.
Right. So this is a question which I think I should know the answer to, but I don't. So can an integrable system doesn't necessarily thermalize, except to a generalized Gibbs ensemble, right? But can it show approximate chaotic characteristics for a subset of correlators?
Well, this is something that's been discussed a little bit in the literature, and there are, in some integrable theories, you can compute out-of-time order correlators for different operators, and sometimes you find that they exhibit the behavior that you would expect in a chaotic theory. Like the out-of-time order correlate, some out-of-time order correlators go to 0. but it isn't the case for all of the operators. And somehow the diagnostic of chaotic theory is that the out-of-time order correlators should go to 0 for pretty much any choice of operator that you use, not just for special ones. Actually, related to this, I would like to make one comment which I think is, there's some, just correcting a minor misconception, which is that the butterfly effect, as it relates to out-of-time order correlators, is not the statement that the out-of-time order correlators have exponential growth. The butterfly effect is the statement that at late times they go to 0. So that's the statement that like every operator can have a large influence on any other operator. It doesn't have to be exponential. And this is the same way with the butterfly effect in our own world. Like the effect can spread in a local theory, it can spread in a ballistic way. And that's the way that you expect it to behave in quantum chaotic systems as well.
Okay. Any questions specifically for Douglas? Sandeep. Need it, Mike?
Sorry, if I can just come back to some of your last comments
Yeah.
about the UV sensitivity.
Yeah.
Are you saying that in a case where we have a unitary theory which is at low energies, say dual to a JT model, as might happen if you have a near extreme Reisman-Nordstrom
Yes.
in a more complete
Yes.
theory? You're saying there the trumpets won't contribute because of these small necks where things go around and break them off?
So you could imagine writing basically yes, you could imagine writing a trumpet geometry there, and if you get your JT gravity theory from some higher dimensional theory, then there will be some matter fields propagating in 2 dimensions, like the KK modes or whatever else you have. And those matter fields will give a divergent contribution in the region of moduli space where the trumpet is long and thin. So I don't know how to even begin calculating the contribution of the double trumpet in such a theory. In 3D pure gravity, you're okay, but for this type of theory, I don't know. And that's the kind of thing that makes me a little bit hopeful that there could be something about the UV properties of the bulk theory that distinguish these. And it seems possible that the answer is just that it's only very stupid theories of gravity, like JT gravity or, well, maybe 3D pure gravity, but maybe not even that. It's only very stupid theories of gravity that are dual to disorder averages, and that the better theories of gravity are dual to specific quantum systems. So that seems very much possible.
Thank you.
The Euclidean wormholes of Maldacena and Maus have many negative modes, which I interpreted as a suggestion that they don't contribute to the Euclidean path integral, and in fact it indicates they're breaking up.
And in case they what, sorry?
The negative modes indicate that the solutions break up, which in fact sort of connects to what you're saying there.
Well, yeah, the analysis of this is pretty complicated, and I think, at least in pure gravity, I don't think that the geometry that I showed there has negative modes. So, on the other hand, I'm not sure that it would be a problem. Like, you can still imagine doing the path integral over some other contour.
Well, at least in Coleman's days, many negative modes meant they were not meant to contribute to the path integral. It's the Euclidean wormholes with axions, the regular solutions. We've shown they have many negative modes.
Well, yeah, this is part of the complication of finding these Euclidean wormholes, is that it's harder than you might think to find solutions, and even harder to find stable solutions. And maybe I'm drawing the wrong lesson from this, but it seems like in JT gravity, it wasn't even a solution to begin with. So I'm not sure that we should constrain ourselves so much to those types of configurations. I think I should have expressed more uncertainty about this during the talk. I feel quite uncertain about all of these issues. So.
That's right. We have little time, so can I invite all the speakers to join? Have a seat. I think we have microphones for everybody.